Hi folks, we're going to take a look at number 9 from page 363. So here they want us to resolve a 10 Newton force vector into two perpendicular components. And one of these components has to make an angle of 15 degrees with that force vector. Okay, so let's understand what they're asking. So this word resolve here, so when we resolve a vector, essentially what we're doing is we're representing it as the sum of two other vectors. Okay, and in this case here, they want us to represent it as a sum of perpendicular vectors, and each of those are called components. Okay, now I'm just going to draw some general vector here. Okay, I'll let that represent our 10 Newton force vector. So here, magnitude of this force vector is 10. Okay, and I actually purposely drew it so that when I draw one of my components, it's not going to be horizontal and vertical. So I really want to press the idea that while we often use horizontal and vertical components, we don't necessarily have to. Okay, so I need one of these components to be 15 degrees from my vector. So I'll draw something that looks reasonable. Okay, so that's going to be one component. Makes an angle of 15 degrees. Notice here that it's the angle between the vectors placed tail to tail. And I'm going to take this vector and then add a perpendicular vector, okay, to get to the tip of F. Okay, now you might sort of say, well, when we're representing angle between vectors, we don't place them tip to tail, we place them tail to tail. But remember, these vectors here can be moved anywhere we like. So if we want to represent the angle between those vectors, okay, there we go. We'll call this, we'll call this FA and FB. Okay, so I won't use X and Y. We usually use that when we're talking about horizontal and vertical. So this angle here is 90 degrees, and of course, because they're parallel, this must also be 90 degrees. Okay, so essentially what we have is we have a right angle triangle that we're working with because we're breaking it down into perpendicular components, and so we can use good old prime ratio trigonometry like we have in the past. Okay, so what I'm looking for is these two components. Be nice and easy. So here for FA, okay, we're going to be using cosine because we're looking at the adjacent side in this triangle. So the magnitude of FA, and here I think I'm just going to go ahead and write it straight out. It's just going to be 10 cos 15. 10 times cos 15 degrees. Why? Because cos of 15 degrees is just equal to this length divided by 10. Okay, so let's calculate that here. Okay, get that other problem out of the way. 10 times cos 15. Okay, and here we have 9.66. Okay, so the component, which is 15 degrees away from the vector, has a magnitude of 9.66. And now to calculate the perpendicular component, okay, we've got 10 times sine 15 degrees because here we're working with the opposite side. Okay, so 10 times sine 15 degrees, and there we go, we've got 2.59. Okay, and that's it. These are the magnitudes. Now in terms of, giving these components as vectors, I guess, we could say FA is 9.66 newtons, and it's 15 degrees from the force vector, and then FB is going to be 2.59 newtons, and I guess we can describe it in this way. If that's 15 degrees, well, 90 minus 15 is just going to be 75 degrees from the force vector. Okay, or I suppose we can also say just perpendicular to that other component. Okay, so there you have it. So when we're resolving a vector, we're just writing it as the sum of two other vectors. Okay, most often we'll write that as the sum of two perpendicular vectors, but they don't necessarily need to be horizontal and vertical. Now I could have drawn the picture so that it did look that way, but it doesn't have to be. Okay, that's it for this one.